Good morning, ladies and gentlemen. My name is Shengwen Tu. I'm from Xi'an University from China. And the title for the presentation is about the ductile fracture response for pipeline stairs with the Lüders plateau. Sorry. Yeah, the co-authors are Xin Liu and Professor Guangxu Cheng. The structure of the presentation is as follows. First, I will shortly introduce the background of this research, and then I will introduce the discontinuous yielding, and then the resistance curve of ductile materials. In the following will be the Gaussian density model we used to simulate character propagation, and in the last will be the results and the main conclusions. In recent years in China and in other countries, there are several accidents happened due to the fracture of gas weldment. In the two pictures in the bottom, in the left side is the fracture of gas weldment of X18 pipelines used for the natural gas transportation, and the right part, the right picture is about the gas weldment of fracture of X18 pipelines used for CO2 transportation in US. We can see that the fracture of the gas weldment is the fracture of the whole cross section. And the situation for China is that the total mileage of X18 pipelines in China is more than 70,000 kilometers, which is more than 2 times of the X18 pipeline, the total mileage of X18 pipelines out of China. So for Chinese, it is very important to understand the fracture behavior of gas weldment. And when coping with the gas weldment, there are several challenges to be conquered. For example, the microstructure of gas weldment is very complex. We have the white matter, we have heat affected zone, we have the base material. So the inhomogeneous material, inhomogeneous structure is a problem. Another problem is that the mechanical properties in the gas weldment is scattered. And when we would observe the fracture surface of the gas weldment, we can observe the ductile fracture and bridge fracture. Sometimes from the cross section, it is totally ductile, but sometimes it is a combination of ductile fracture and bridge fracture. In addition, we can see in the left picture that the correct parts in the gas weldment is also very complex. We have different fracture mode in the gas weldment. Therefore, it is very difficult to solve this problem. However, in our present work, we try to understanding the influence of Lüders plateau on the ductile fracture of gas weldment. And the Lüders plateau was found in the tensor test, usually for low strength stairs. During the tensor test with the DSA technology, we can observe the propagation of Lüders band formed at the two ends of the specimen and then propagate to the middle of the specimen. During the propagation of the Lüders band, we can find the flat stress, the flat stress on the stretching curve. And the Lüders plateau was influenced by many factors. For example, the grain size of the material and the testing temperature, and also the strain rate. And the Lüders plateau was usually observed in the low carbon steel. However, for the X18 pipeline steels, it was observed in both the wild matter and heat affected zone, and also sometimes even in the base materials. To simulate to investigate the influence of Lüders plateau on ductile fracture, experimental research is very difficult because we cannot control the plateau length. So we have to use numerical simulation. For the Lüders plateau model, we have two models. One is the so-called up-down up model, but I slightly changed the model here because in the up-down up model, here I present only the flow stretching curve, which is that the horizontal axis is the equivalent plastic strain, and the y-axis is the normalized stress, which is the flow stress normalized by the yield stress. And we have for the up mode, we have 3 parameters. One is the softening modulus, and another parameter is the plateau length, and the third one is the stress active. And another model is the so-called flat model, which means that we keep the plateau stress equaling to the yield strength. And for the up mode, if we set the softening modulus equal to 0, then we get the flat model. So in the present research, we use both the flat model and the up model in our work. And some researchers investigated the influence of Lüders plateau on the mechanical behavior. For example, on the bending behavior of tubes with the up mode. Because with the up mode, we can observe the propagation of Lüders band. And some researchers investigated the influence of the Lüders plateau on the correct driving force with the flat model. And from their results, we can say that with the increase of the plateau length, the correct driving force increased. And however, there are very limited research on the influence of Lüders plateau on the ductile correct growth resistance curve. So in our work, we try to do some investigation. And here is an example of the R resistance curve for ductile materials. The x-axis is the correct propagation length, and the y-axis is the fracture toughness, which usually is J integral or the correct tip opening displacement. And as we will know that the ductile correct growth resistance curve depends significantly on the correct tip constraint. The higher the correct tip constraint, the lower we can obtain the R resistance curve. So to simulate the correct propagation, we use the Gaussian damage model, and this is the yield function of the model. And the correct propagation is the result of the void nucleation, void growth, and coalescence. And the void growth and coalescence is controlled by this equation. And in our pneumatic model, we choose the modified boundary layer model, and this is the match of the due to the symmetric of the specimen, we only use the half of this model, and the boundary condition is controlled by the displacement field outside of the specimen surface, and this is the control the governing equations of the displacement field, and along the correct tip, we have very fine match here, and we will obtain the correct tip opening displacement from the point just behind the initial correct tip. Sorry, it's not good. Yeah, and also along the correct propagation, the element length is the size of the element length is LC. And in our work, the correct propagation length is normalized by the element length here in the results. And first, I will show some results with the flat model. We have two reference cases. One is this is the flow stress curve. We have two reference cases. One is the material without Lüders plateau, and then another one is that for the blue case, it is called the perfectly plastic material, which means that the plateau length is infinite. And we have another three cases with the flat Lüders plateau model by setting the plateau length equal to 0.01, 0.02, and 0.03. And in the right side, we present the result of the correct growth resistance curve, and we can see that we have this without Lüders plateau, we can get the black curve, and with the perfectly plastic material, we can get this blue curve. And for the material with the Lüders plateau, we can see that with the increase of the plateau length, the crack growth resistance curve shift down first and then shift up with the increase of the plateau length. This is very interesting, and we try to we find the secret behind. And we also investigate the influence of the softening modulus on the resistance curve. We can see that in this slide we present the results for the plateau length equal to 0.01, 0.02, and 0.03. We can see that we have these two reference cases, and for the material with the same plateau length but different softening modulus, we can see that the crack growth resistance curve almost overlap to each other, which means that the effect of the softening modulus on the crack growth resistance curve is negligible. But which plays an important role is the plateau length. To find out the influence of the effect of plateau length on the crack growth resistance curve, we checked the weight growth at different crack lengths. For example, for the case with the plateau length equal to 0.01, we at different crack growth, we can find that the weight growth is faster than the reference case for the material without Lüders plateau, and the weight growth is slowest for the material with infinite with the perfectly plastic material. So we can see that the plateau length changed the weight growth rate, and this is for the case with the plateau length equal to 0.02. We can also find that because at different crack lengths, the weight growth differs slightly to the reference case for the material without Lüders plateau. Therefore, the resistance curves almost overlap to each other, except the reference case with infinite plateau lengths. And for the plateau length equal to 0.03, we can find out that the weight growth is postponed when the crack growth is larger than 1 millimeter, and we can see that the crack growth resistance curve is higher than the reference curve with the material without Lüders plateau, and we can see that the Lüders plateau length control the crack growth resistance curve, and then we check the crack tip constraint. However, during the crack propagation, the constraint ahead of the crack tip changed. Therefore, we used the average value of the structure activity ahead of the crack tip, and the result is shown here. We can see that for at different crack lengths, the crack tip open displacement value shows opposite trend to the average value of structure activity, which means that the introduction of the Lüders plateau changed the crack tip constraint. That in that case, the ductile crack growth resistance curve was also changed, and we also investigated the influence of the Lüders plateau coupled with the strain hardening parameter and the initial weight volume parameters. However, the influence is not significant. Yeah, here comes the conclusion. In this work, I want to introduce that the Lüders plateau length do influence the crack growth resistance curve for the parameters we investigated in our work. Yeah, that's the presentation. Thank you very much.